Our solar system has always felt like a familiar, well-understood home. We know its planets, we track its asteroids, and we have watched its comets like Halley's trace their predictable paths across our skies for centuries. We understand these comets. They are dirty snowballs, ancient leftovers from the dawn of our own system that spring to life when they near the sun, growing magnificent tails of gas and dust that always without exception point away from the sun's powerful light and wind. We felt we had the rules figured out. Then an object from another star system, entirely 3I Atlas, entered our neighbourhood. And on a single day in November 2025, it shattered all of those rules. An event has just occurred that is so profound, so utterly bizarre, that scientists are scrambling for an explanation, forcing us to ask a question that was once confined to science fiction. Is this object truly natural? The story of this revelation begins not with a billion-dollar space agency, but with the patient, watchful eyes of dedicated astronomers. On the 9th of November 2025, Frank Nebling and Michael Biener, two observers known for their meticulous work, were imaging the interstellar visitor. 3I Atlas had been an object of intense curiosity since its discovery. As only the third known interstellar object, it represented a rare chance to study a piece of another solar system up close. But on this night, what appeared on their screens was not the simple fuzzy dot of light they had been tracking. It was something that at first must have looked like a data error, a glitch in the sensors. It was too large, too complex, and too structured to be real, but it was real. The images processed and confirmed revealed something astonishing. The object was not just passively drifting, it appeared to be actively and violently projecting three enormous structures, three jets of material on a scale that boggles the mind. This is where the discovery moves from interesting to impossible. Let's break down what they saw. The most baffling physics-defying features were two distinct plumes of material that the observers labelled anti-tails. These two jets were streaming toward the sun. This simply should not happen. The sun is a giant engine of light and energy constantly blowing a solar wind of particles outward in all directions. For a comet, this is a one-way street. The heat vaporizes the ice, and the solar wind pushes the resulting gas and dust away. And to find a structure pointing into this headwind is like seeing the smoke from a fast-moving train flowing forward in front of the engine. It makes no physical sense. Yet here they were, two colossal beams, each one stretching for approximately 1 million kilometers, aimed directly back at the star whose very energy should be making their existence impossible. 1 million kilometers is a distance almost too vast to comprehend. It's about 2.5 times the entire distance from the Earth to our moon. But 3 Atlas was not finished. While two tails pointed in the wrong direction, a third structure did the opposite. A single powerful beam of material was seen shooting away from the sun as one might expect. But this was no normal dusty tail which usually spreads out like a fan. The report described this as a columnated beam. That single word changes everything. Columnated means it was focused tight and narrow, like a searchlight or a laser beam. A natural comet's tail just sprays, it doesn't focus. This focused beam was even more monstrous in size than the anti-tails, extending for an unbelievable 2.85 million kilometers. That is 2,850,000 kilometers. This single beam projecting from a tiny dark object was long enough to cross the span between the Earth and the Moon more than 7 times over. To understand why this discovery is so world-changing, we must compare it to what we saw before. Just a few months ago, in July 2005, astronomers used the mighty Hubble Space Telescope to get our best look yet at 3I Atlas. Hubble is our most powerful eye in the sky, and what did it see? It saw a coma, a small fuzzy halo of gas and dust around the object. This was exciting as it proved the object was active, but it was also normal. It was what we expected to see. The structure revealed in November is on a completely different level. The sheer scale of these jets is 1,000 times larger than the simple coma Hubble managed to photograph. This implies something terrifyingly powerful. It means that between July and November, this object didn't just get a little brighter. It turned on. It underwent a transformation on a scale we have never witnessed, unleashing energy to create structures that dwarf anything in its class. This is the central mystery. A normal comet is a passive object reacting to the sun. 3I Atlas is acting like an active object. A 2.85 million kilometer focused beam implies a nozzle, a source of incredible directed energy. The 1 million kilometer anti-tails imply a force that can overpower the sun itself. This is not the behavior of a dirty snowball. This is a scale of activity, a complexity of structure that is completely unprecedented. We have no models for this. No natural phenomenon we know of can explain this. The event of November 9th has changed 3i Atlas from an astronomical curiosity into the most profound and pressing anomaly in human history. When we left off, we established that 3i Atlas was a very strange visitor. It looked at first glance like a classic comet. It came from the dark, it got close to the sun, and it grew a spectacular tail. But as scientists watched, they realized this was not a normal comet. The shape was wrong, the behavior was wrong, and as they started to run the numbers, the physics became, well, impossible. To understand why 3i Atlas is such a puzzle, we first need to understand what a normal comet does. Think of a comet as a dirty snowball, a loose clump of ice dust and rock floating in the frozen darkness of deep space. For billions of years it stays quiet. But if its orbit brings it close to our sun, things change. The sun's heat begins to warm the comet's surface. The ice on the comet doesn't melt into water. In the vacuum of space it sublimates. This means it turns directly from a solid ice into a gas, skipping the liquid phase entirely. This gas mixed with dust erupts from the comet's surface in jets like tiny geysers. This cloud of gas and dust is what creates the coma, or the fuzzy atmosphere around the comet. The gas itself usually leaves the comet's surface at a relatively slow speed, perhaps around 0.4 kilometers per second. This is fast to us, but in space it's a gentle puff. Then two forces from the sun take over. The first is sunlight itself, which can actually push tiny dust particles. The second and more powerful is the solar wind. This is a constant hurricane of charged particles streaming away from the sun at incredible speeds, often around 400 kilometers per second. This solar wind acts like a cosmic leaf blower, pushing the gas and dust away from the comet. This is what creates the long, beautiful tail that always points away from the sun, no matter which way the comet is traveling. That is the standard playbook for a comet. It's a simple passive process. The sun heats the ice turns to gas, and the solar wind blows the gas away. 3i Atlas did not follow this playbook. When we apply these rules to what we saw, the entire picture falls apart. The time problem. The first issue is the sheer scale of the tails. The main tail, the one streaming away from the sun, was enormous. But even more puzzling was the anti-tail, the sharp and narrow jet pointing toward the sun. Material in a tail doesn't just appear, it has to travel from the comet to the end of the tail. Scientists can measure how fast the object is moving and how long the tails are, and from that they can calculate how long the engine must have been running to produce them. For the main tail, the one that looked more like a normal comet's dust streak, the calculations showed it was so long that 3i Atlas must have been steadily releasing material for at least 3 months. For the bizarre anti-tail, the rocket-like plume, the numbers showed it required a continuous focused blast lasting for at least 1 full month. This is not how comets work. Comets are not steady, reliable engines. They are lumpy, uneven, tumbling chunks of ice. They spin. As one icy patch faces the sun, a jet might turn on. As it spins into shadow, that jet turns off. Cometary activity is messy, sporadic, and inconsistent. 3i Atlas, by contrast, appeared to be firing its jets continuously day and night for months on end. This sustained long-duration thrust is unlike anything ever observed from a simple icy snowball. The pressure problem. This leads to the second, more baffling issue. Remember the solar wind, that 400 km per second hurricane blowing from the sun? It is the single most powerful force shaping a comet's tail, and it always pushes material away. Yet 3i Atlas had a bright, dense, narrow anti-tail pointing directly into this hurricane. Think about what this means. It's like trying to spit into a Category 5 hurricane and having your spit travel forward in a straight, tight stream. For the material in that anti-tail to win against the solar wind, it couldn't be a gentle puff of gas. It had to be a spit of incredible power. The gas and dust in that anti-tail had to be extremely dense and ejected at a very high velocity, powerful enough to overcome the massive constant pressure of the solar wind. This isn't sublimation. This isn't a dirty snowball warming up. This is a high-pressure focused blast. It behaves less like a comet and more like a rocket engine. The mass problem. The first two problems are strange, but this last one is the knockout blow. It's where the physics becomes truly impossible. When scientists like Avi Loeb at Harvard looked at 3i Atlas, they didn't just see a bright object, they measured how bright it was. From the brightness and density of the dust and gas clouds surrounding it, they could calculate the rate at which the object was losing material. How much fuel was it burning to create these magnificent tails? The number they calculated was staggering. 3i Atlas was losing mass at a rate of 50 billion tons per month. Let's try to make that number real. That is the mass of thousands of the world's largest aircraft carriers. It is a mountain of material being completely vaporized and blasted into space every single month. Now compare this loss to the object itself. Based on how bright the object was before it started its violent activity, scientists could estimate its size and minimum mass. The total estimated minimum mass of 3I Atlas itself was approximately 50 billion tons. Here is the central impossible paradox: 3 Atlas was losing its entire minimum weight every month. We already know from the time problem that this activity was happening for at least 3 months. This means 3 Atlas lost at a minimum 3 times its own estimated starting mass. It's like finding a small campfire that has somehow burned more wood than exists in the entire forest. It simply doesn't add up. There is only one logical physical way to solve this problem. If the object survived this process, its minimum estimated mass must be completely wrong. The only way 3I Atlas could survive losing 50 billion tons of material every month for several months is if it was vastly more massive to begin with. It couldn't be a small typical comet. To have enough fuel to burn that hot for that long, the object must have been enormous. The new calculations based on what it must have lost paint a very different picture. To survive this event, 3I Atlas couldn't have been a small kilometre-wide rock. It must have been a massive body at least 10 kilometres in diameter. This makes it a dwarf planet-sized object, far larger and far, far rarer than a typical comet. We were not watching a dirty snowball. We were watching a massive object violently tearing itself apart with forces that we simply cannot explain with standard cometary science. We have been tracking this incredible object, 3I Atlas, on its journey through our solar system. We've discussed its high speed, its interstellar origins, and its strange flat shape. But now we arrive at the most baffling part of its story. This is the moment where 3I Atlas truly challenged everything we thought we knew about comets. It all centers on one specific event, its closest approach to our Sun, an event astronomers call perihelion. What happened at perihelion wasn't just interesting, it was a complete shock. This part of the journey is what I call the perihelion switch. Think of it like a light switch in a dark room. You know where the switch is, you expect that when you flip it the light will come on. But what if for its entire journey towards the switch the object was completely dark, silent and cold, and then only after it passed the switch it suddenly burst into brilliant roaring life? That's precisely what we saw. This discrepancy, this sharp before and after, is the single biggest puzzle we face with this object. Let's set the timeline. The date was October 30th. This was the day 3I Atlas reached perihelion, its closest point to the Sun where the solar radiation is the most intense. Now, as any comet gets closer and closer to the Sun, the heat increases dramatically. We expect to see activity. We expect the ice on its surface to turn directly into gas, a process called sublimation. This is what creates the beautiful tail, the coma, or fuzzy atmosphere around a comet. It's the very definition of a comet. The closer it gets, the more active it should become, spewing out dust and gas in a long, flowing tail. But 3I Atlas did almost nothing. It was eerily quiet. Our telescopes trained on it with intense focus saw, well, not much. It was just a point of light, a dark rock reflecting sunlight. There was no significant tail. There was no massive coma. This was deeply strange. Here it was plunging towards the hottest part of its entire journey, and it was behaving like a dead inert asteroid. This lack of activity, this unusual quickness was a huge problem for the icy snowball theory. If it was a comet, where was the gas? Where was the dust? It was travelling for years, getting closer and closer to the solar furnace, and yet, silence. It was almost as if it was holding its breath, waiting for something. This silence before October 30th is the first clue that something was very, very different about this visitor. Then it passed perihelion. It swung around the Sun and began its long, fast journey back out into the darkness of interstellar space. And that is when the switch flipped. It wasn't a gradual increase, it was a sudden change, a violent transformation. Almost immediately after its closest approach, our telescopes lit up. Enormous, powerful jets of material suddenly erupted from the object. It wasn't the gentle, fuzzy glow of a typical comet. These were focused, massive plumes of gas and dust blasting away from the surface at high speed. It was like watching a dormant volcano instantly explode. The change was so stark, so abrupt, that flipping a switch is genuinely the best analogy we have. Before perihelion, a quiet dark rock. After perihelion, a dynamic active object firing off huge jets. Why? Why now? Why not before, when the heat was also intense? Why not during the moment of maximum heat? Why only after it had passed the sun and was technically starting to cool down? This timing makes almost no sense for a simple natural comet. A comet should be most active at perihelion, or just before as the heat builds to its absolute peak. 3i Atlas waited until the show was supposedly over, and then it decided to erupt. This observation is the central mystery. It's the piece of data that breaks all the standard models. These weren't just little puffs of gas. The sheer volume of material being ejected was staggering, causing the object to visibly accelerate. This observation is what forced the scientific community to split into two very different camps. How do you explain an object that waits until after it passes the fire to suddenly burst into flame? Science, by its nature, must always look for a natural explanation first. And there is one. It's a plausible natural explanation, though it requires a bit of a special circumstance. The idea is that 3i Atlas wasn't a uniform snowball. Imagine instead that the volatile ices, the really explosive stuff like frozen carbon monoxide or nitrogen, weren't on the surface. Imagine they were buried deep inside the object, trapped under a thick insulating crust of rock or more stable water ice. As 3i Atlas approached the sun, this outer crust heated up. But like heat travelling through the wall of an oven, it took time for that thermal energy to soak through the rock and reach the core. According to this theory, the heat finally reached those buried pockets of volatile ice right around the time of perihelion. When the intense heat finally hit those pockets, they didn't just melt. They flashed instantly into gas, building up incredible pressure. Boom! The pressure became too much and the crust ruptured. This would cause a massive explosive outgassing, just like the powerful jets we saw. This explanation works sort of. It explains the suddenness, it explains the violence, but it also relies on a lot of coincidence. The ice pockets had to be buried at just the right depth for the heat to reach them at just the right time immediately after perihelion. It's a very convenient coincidence. And it doesn't fully explain why the object was so incredibly quiet for so long before that moment. It's a possible answer and many astronomers hold to it, but it feels complicated. It requires a very specific and somewhat lucky internal structure. Is it the most likely answer? For some, the timing is just too suspicious. This brings us to the alternative explanation, the one championed by Professor Avi Loeb. This is where we step outside the box of conventional astronomy. Loeb asks a simple, powerful question. What if we are looking at this backward? What if the sudden appearance of jets wasn't a natural explosive accident, but a deliberate controlled action? What if 3i Atlas is not a comet at all but an artificial object? What if this was a propulsion system firing not a natural sublimation? This sounds like science fiction, but let's look at the numbers. When a comet's ice sublimates, the gas drifts away relatively slowly, maybe at a few hundred meters per second or perhaps 1 kilometer per second. But what if the material we saw was being ejected at much higher speeds? Let's think about our own technology. A chemical rocket like the ones that launch our astronauts has an exhaust velocity, the speed the gas comes out the back, of about 3 to 5 kilometers per second. An ion engine, a highly efficient engine we use for deep space probes, pushes out its propellant even faster at speeds between 10 and 50 kilometers per second. This speed, the exhaust velocity, is crucial. It's what we call specific impulse. The higher the exhaust velocity, the more push or thrust you get for the same amount of fuel. It's the difference between trying to move a boat by throwing thousands of ping-pong balls off the back versus firing a single heavy cannonball. The cannonball is far more efficient. Here is the most important part of this hypothesis. If the jets from 3i Atlas were a high-velocity exhaust, like from a rocket or an ion engine, the implications are profound. A natural comet, to produce the thrust we saw, would have to shed a massive amount of its total mass in the form of slow-moving gas. But if the exhaust is moving at, say, 30 kilometers per second instead of 1 kilometer per second, you need far less fuel to get the same push. The math shows that the mass of fuel required would be 1 to 2 orders of magnitude less. That's a fancy way of saying 10 to 100 times less fuel. This means that instead of needing, say, 30% of its total mass to be ice that boils away, it might need less than 1% of its total mass to be propellant. This makes the whole process vastly more efficient. It means a small, thin, lightweight object like the flat pancake shape we observed could absolutely perform this maneuver without destroying itself. It could fire a small amount of mass at extremely high speed to give itself the push it needed. So this is the core of the dilemma. We have two possibilities. One is a natural comet, but a very, very strange one with a special internal structure that just happened to explode at the perfect time to explain its acceleration. The other is a technological object, a light sail or a probe that fired its engines after it used the sun's gravity to make its turn. The problem in its simplest form is this: the data does not fit the model of a normal typical comet. The behaviour we observe, the silence before the violent eruption after, is an anomaly. It doesn't match what we expect. And when the data doesn't fit the model, you have two choices. You can try to force the data to fit, making your model more and more complicated, adding more and more coincidences, or you can accept that your model might be wrong. This is what science is all about. 3i Atlas forced us, whether we like it or not, to ask new questions. It challenges our assumptions about what's possible, and it demands that we keep our minds open to every possibility, no matter how extraordinary. In the grand story of the cosmos, we have always seen ourselves as residents of a secluded island. Our solar system was our entire world, a closed-off environment with its own set of rules and residents. That all changed in 2017. The sky was torn open not by a physical force but by an idea. We suddenly and shockingly realized we have visitors. The study of the space between stars, once a purely theoretical field, has become a dynamic and urgent game of catch and release. We are now in the era of interstellar observation, and we are being defined by three specific visitors that form an extraordinary trio. The first was Oumuamua, detected in 2017. It was the first messenger, and it was deeply, profoundly weird. It was small, perhaps the size of a city block, and shaped either like a cigar or a flat pancake. It tumbled strangely through space. Most bizarrely, as it looped around our sun, it sped up. It accelerated in a way that gravity alone could not explain. There was no visible tail of gas or dust, no cometary activity to explain this non-gravitational push. This single baffling fact opened a Pandora's box of speculation. Was it a natural but unknown phenomenon, like a hydrogen iceberg evaporating? Or was it, as some scientists boldly suggested, something else? Oumuamua was a riddle that shot through our system and disappeared back into the dark, leaving us with more questions than answers. Then, just 2 years later, in 2019, came 2i Borisov. This visitor was a tremendous relief to astronomers. It looked like a comet. It acted like a comet. It had a clear tail of gas and dust. Its chemical makeup, which we could study, looked very similar to the comets from our own solar system's outer edges. Borisov was normal. It was a crucial data point suggesting that perhaps Oumuamua was the exception, not the rule. It proved that other solar systems make comets just like ours. Borisov provided a baseline, and now in 2025 we have 3i Atlas. This object shatters the simple weird versus normal debate. It is not like Oumuamua, it is not like Borisov. It has established itself as an entirely new class of object. The most defining feature of 3i Atlas is its sheer overwhelming scale. It is not a single object, it is a phenomenon. It's a procession, a blizzard, a vast complex cloud of fragments and streams of material stretching for millions of kilometers. It is a massive object that has come apart and we are witnessing its disintegration. Its size and its behavior place it in a category of its own, superior in scale to anything that has come before. This trio sets the stage for the most exciting observational race in modern astronomy. The historical context is clear one riddle, one normal baseline, and one massive new mystery. For months, 3i Atlas was lost in the glare of our own sun. Its path took it behind our star from our point of view, making it impossible to see, but that time is over. The object has now moved 30 degrees away from the sun in the sky. This is the signal the astronomical community has been waiting for. It is the starting gun for the race. At 30 degrees, the sun's blinding light is no longer a factor. The visitor is emerging into the dark of the night sky, and for the first time our ground-based observatories can get a clear, sustained look. The mission for every major telescope on Earth is now simple: get every photon, every piece of data we possibly can before it slips away. The window is open, but it will not be open forever. This is not a task for a single telescope, it is a global campaign. Our first and most urgent task is to measure the composition of the streams. We do this by reading the light. Using instruments called spectrographs, astronomers can spread the faint light from the object's cloud into a rainbow, a barcode. In this barcode, different chemicals leave their own unique fingerprints. We are hunting for the chemical signatures of water, carbon, monoxide, nitrogen, and other ices. Is this object made of the same stuff as our own comets like Borisov? Or does it contain a ratio of materials that points to a different kind of planetary nursery, a different chemical history from our own? Second, we need to understand the velocity and density of the streams. We are not just looking at a static cloud, we are watching a disaster unfold in slow motion. We need to measure how fast the fragments are moving away from each other. This will tell us about the forces that blew it apart. Was it a gentle disintegration as the sun's heat slowly vaporized its ices, or was it a more sudden, violent event? The density of the streams, how thick the clouds of dust and gas are, tells us how much material has been lost. This allows us to work backward to estimate just how colossal the original parent body must have been before it began to break. Finally, we are searching for the fragments. 3i Atlas is not a single entity. It is a fleet of icy boulders all flying in formation. Our most powerful telescopes are now trying to find the largest remaining pieces, the core of the object that might still be intact. These largest chunks are the most valuable. They are the primary source, the ground zero from which all the streams originate. Finding them and tracking them is our top priority. All of this work is leading up to a key date, December 19th. On this day, 3i Atlas will make its closest approach to Earth. It will not hit us, it will not even come close. Its closest pass will be a very safe 269 million kilometers away. But in astronomical terms, this is a golden opportunity. This is the moment when the object will be at its brightest, its largest, and its easiest to study from our perspective. On and around December 19th, every telescope that can see it will be watching. It is our best and perhaps final chance to get the highest resolution data. After this date, 3i Atlas will begin its long, lonely journey back out of the solar system, moving away from Earth and fading in brightness with every passing day. It will recede, becoming a faint, unresolved dot, and then nothing at all. It will never return. We have this one shot. This brings us to the great open question. What exactly are we looking at? We are staring at a mystery, and the answer will likely fall into one of three possibilities. The first is that this is simply an extraordinary natural phenomenon. This is the most likely, most scientific answer. We are seeing a massive ancient comet, perhaps a billion-ton chunk of ice and rock that was ejected from its home star system millions of years ago. It drifted through the interstellar cold and by pure chance tumbled into our solar system. Its fragile icy structure, never before subjected to the intense heat of a star, like our sun, simply could not handle the thermal stress. It cracked, shattered, and is now outgassing on a spectacular scale. It is a beautiful, violent, and entirely natural event. The second possibility is more poetic, but just as plausible. We are witnessing the fragment of a world. What if 3i Atlas is not just a comet? What if it is a piece of something larger? In the chaotic early days of other solar systems, planets collide. Moons are shattered. Perhaps what we are seeing is a refugee from such an ancient catastrophe, a piece of an exoplanet, a Pluto from another system that was destroyed and cast out. If this is true, its chemical composition is not just a sample of a comet. It is a sample of the crust or mantle of another world. And then there is the third lingering question, the question Oumuamua forced us to ask: is it something else? This is the whisper at the edge of science, the placeholder for the unknown. When we see an object of this scale, an unnatural origin seems profoundly unlikely. But the patterns, the data, the sheer strangeness of our interstellar visitors first, Oumuamua, and now this force us to keep an open mind. Science is not just about confirming what we know, it is about bravely investigating what we do not. We stand at a unique moment in history. The barriers between the stars are dissolving. We are no longer an isolated island. We are a port of call, and the ships, strange and silent, have begun to arrive. 3i Atlas is the largest ship we have ever seen, and the race is on to read its logbook before it vanishes into the ocean of space forever. As 3i/Atlas completed its hairpin turn around our sun, surviving the most intense part of its journey, astronomers kept their telescopes pointed directly at it. They were watching for any changes, any new clues, and what they saw next turned the entire mystery upside down. This wasn't just a faint puff of gas anymore. What our best telescopes, including the Hubble Space Telescope, detected was shocking 7 distinct separate jets of material were blasting away from the object. Think about that for a moment. A normal comet, when it gets close to the sun, heats up and releases gas and dust. This creates a tail, or sometimes two, a dust tail and an ion tail, but this is usually a broad single plume. What we were seeing from 3i/Atlas was completely different. It was not one big cloud, it was 7 specific narrow beams, like 7 separate rocket engines all firing at once. It was as if you looked at a speedboat and instead of one wake you saw 7 perfect parallel wakes fanning out behind it. This was not normal. This new discovery immediately led to a very logical, very scientific question, one voiced by Professor Avi Loeb and many others: did 3I/Atlas break apart? This is, after all, the most common sense explanation. Comets are fragile. They're often described as dirty snowballs. When they get too close to the sun, the intense heat and gravity can cause them to fracture and disintegrate. If the main body of 3I/Atlas had shattered into 7 or more large pieces, each individual piece would then act like its own new comet. Each fragment would have fresh ice exposed to the sun, and each fragment would start spewing its own jet of gas. Seeing 7 jets therefore strongly implied there were now 7 or more sources. The case seemed simple: the object had died breaking up under the solar stress. But astronomy is rarely that simple. This observation created a profound and immediate paradox. While our telescopes were sharp enough to see the 7 jets of gas, we could see no clear evidence of the fragments themselves. This was the central puzzle. If the object had broken into 7 large pieces, we should have been able to see them. Hubble has seen comets break apart before, like Comet Shoemaker-Levy 9, which famously shattered into a string of pearls before hitting Jupiter. We can see those pieces, but with 3I/Atlas, there was nothing. We saw the smoke, but we could not find the fires. How could you have 7 distinct effects, the jets, without being able to see the 7 distinct causes, the fragments? It was a contradiction. The object was behaving as if it were in multiple pieces, but it still looked like it was a single solid object. This forced scientists to come up with other ideas. This led to hypothesis number 1, a partial disintegration. Perhaps the object didn't shatter into big visible chunks. Maybe instead it just crumbled. Imagine the main body staying in one piece, but its surface began to crack and shed huge amounts of smaller debris, like a loaf of stale bread dropping millions of crumbs. These clouds of tiny fragments would be too small to see individually, but together they would be hit by the sun and release massive amounts of gas, creating the jets. Another version of this hypothesis was that the object's outer crust didn't crumble, but instead cracked open in 7 different places. These new cracks would expose fresh buried ice volatiles that had been protected to the raw heat of the sun for the first time. This would cause a violent focused outgassing, creating the jets we saw. This idea was attractive because it explained how you could get 7 jets from a single object. But this crumbling theory had a very big problem. In fact, it had 2. The first problem was the duration of the jets, and the second was their energy. When a comet cracks or crumbles, the event is usually very fast and explosive. You get a sudden bright flash, a big burst of material, and then it fades away relatively quickly as that newly exposed material is used up. But that is not what happened with 3I/Atlas. These 7 jets didn't just flash and disappear, they were stable. They kept going, streaming material into space for a long period. They were sustained. Furthermore, the amount of energy being released was enormous. When scientists calculated the force needed to push this object, which we discussed in part 4, and then looked at the sheer volume of material in these 7 new jets, the numbers just didn't add up. A simple passive event like the sun boiling off some newly exposed ice seemed insufficient to explain the power and stability of these jets. It would be like striking a match and having it suddenly roar like a jet engine, and then continue to roar for hours. The effect was far too large for the proposed natural cause. This is where the debate became truly divided. The conventional explanations were failing to match the observations. The disintegration theory didn't work because there were no fragments. The crumbling surface theory didn't work because the jets were too powerful and lasted too long. So this led to hypothesis number 2. This was an active process. This is the line of thinking that Avi Loeb and his colleague Shmuel Bialy have explored. What if this was not a passive event at all? What if the jets were not a sign of the object dying and breaking apart, but rather a sign of it doing something? This hypothesis suggests that the process was not one of simple sublimation, where the sun just boils ice off a rock. Instead, it was some kind of deliberate or controlled activity. This, of course, implies technology. It implies the object was not a dead piece of rock, but a functioning machine. In this view, the 7 jets were not random cracks. They were perhaps vents or engines deliberately releasing material. Why would it do this? Perhaps to control its temperature after its close pass with the sun. Perhaps it was deploying smaller probes. Or perhaps, as Loeb has suggested, it was a light sail turning on its propulsion. This explanation, as extraordinary as it sounds, has one major advantage: it perfectly fits the data that natural theories struggle with. It explains how you can have 7 specific jets without any fragments. It explains the high energy of the jets and engine is more powerful than a passive vent, and it explains the long duration a machine can stay on for as long as it has power. This is the heart of the controversy. We are left with two choices. We can either assume our understanding of comets is completely wrong, and that they can somehow produce 7 high-energy, long-lasting jets from a single body without breaking apart. Or we must consider the fantastic possibility that this object was not a comet at all, but was operating under its own power. When we stop assuming that 3I Atlas was just a passive dead rock, the entire picture changes. If we dare to analyse this object not as a comet, but as a craft, all the strange data points suddenly look less like mysteries and more like deliberate design choices. The key is to apply the basic logical rules of engineering and spaceflight. If humanity were to design a vessel to cross the vast cold emptiness between stars, how would we do it? First, you would not build a ship that burns fuel for the entire journey. The energy requirements would be staggering, far beyond anything we can currently imagine. A logical interstellar probe would be built for one thing above all else: efficiency. It would spend the vast majority of its journey, perhaps millions of years, in a state of deep hibernation. This would be a sleep mode on the most profound level. All non-essential systems would be powered down, preserving precious energy, and just as importantly protecting delicate components from the long, wearying drag of time, the constant bombardment of cosmic rays, and the threat of micrometeorite impacts. A dead ship is a safe ship, but this deep sleep wouldn't be forever. The probe's systems would be programmed with a single crucial trigger: the approach to a star. Why a star is an oasis in the cosmic desert? It offers 2 critical resources that are absent in the interstellar void: massive amounts of energy and a powerful gravity well. As the probe falls toward the star, it can deploy collectors, whether solar panels or perhaps more exotic devices, to recharge its power systems. This wake-up call would allow the ship to draw in enormous amounts of energy, rebooting its primary computers, running diagnostics to check for damage after its long sleep, and most importantly preparing its engines. The star's gravity is not just an obstacle to be avoided, it is a tool to be used. This brings us to the second principle: orbital mechanics. If you are a spacecraft and you need to change your path, timing is everything. You cannot just fire your engines whenever you want and hope for the best. There is one golden moment during any close approach to a massive body like a star, and that moment is called periapsis. Periapsis is simply the name for the point in the orbit where the object is closest to the star. At this exact moment, 2 critical things are true. The star's gravity is pulling on the object with maximum force, and the object itself is moving at its absolute fastest speed. If you fire your engines at this one perfect moment, you get an incredible multiplying effect on your fuel. A small, efficient push when you are already moving at your fastest speed results in a massive change to the other side of your orbit. It is the single most efficient way to get the biggest bang for your buck in terms of fuel. If you try to make that same turn from the star where your speed is slow, you would need to burn perhaps 100 times more fuel to get the same result. It's the difference between gently nudging a canoe and trying to stop a freight train. If 3I Atlas were an active probe, this is exactly when we would expect it to fire its engines. It would use this golden moment at periapsis to perform a major course correction, perhaps to slow down and enter our solar system, or more likely to use our sun's gravity like a slingshot. A gravity assist to aim for its next target, star flinging itself toward a new distant destination without spending another 1,000 years in transit. This is where the 7 mysterious jets become so fascinating. A natural comet releasing gas does so randomly. The sun heats a patch of ice, that ice turns to gas and bursts out, and the comet tumbles. It's messy, chaotic and inefficient. But the 3I Atlas event wasn't just a single messy puff, it was a series of distinct plumes. What if those 7 streams were not accidental vents at all? What if they were vectored thrusts? In modern rocketry, vectored thrust is when an engine can pivot or gimbal its nozzle to precisely direct the flow of exhaust. This is what allows a rocket to steer. An even more advanced system, however, would use multiple fixed engines that fire in precise computer-controlled combinations. If you have several thrusters pointed in slightly different directions, you can perform incredibly complex maneuvers. This isn't just about steering, it's about stability. Firing a single massive engine on a craft that has been tumbling through space for millennia is a recipe for disaster. You would lose control instantly. A system of multiple smaller thrusters like these 7 jets would allow the craft's computer to first stabilize itself, cancelling out any spin or tumble. Once stable, it could fire them in a coordinated sequence to apply a very precise controlled push in a specific direction. The number 7 might even be for redundancy. If 1 or 2 thrusters failed after their long sleep, the others could compensate. This would be the signature of a highly sophisticated propulsion system executing a planned orbital maneuver. This leads us to the final crucial question. How could we ever tell the difference? How could we distinguish a natural comet breaking apart from an artificial engine firing? The answer lies in the behavior of the evidence over time. If this was a natural event like the comet simply spinning so fast that it tore itself apart, or a trapped pocket of ice exploding, we would expect to see specific signs. Nature is messy. A comet breaking apart is like a building demolition. We would expect to see fragmentation. The main body would be surrounded by a growing cloud of smaller debris, and all these pieces would slowly drift apart, each following its own slightly different path. We would also expect the jets themselves to be temporary. They would puff out and then they would diffuse. The gas and dust would spread out into space and simply fade away as the pressure was released. The show would be over, quickly leaving behind a messy trail of evidence. But if this was an artificial event, the signs would be completely different. An artificial system, by contrast, is clean. We would look for anomalies that persist. Instead of fading away, the jets might maintain a steady, controlled stream for a much longer period than a natural pocket of gas could sustain. Or even more telling, they might stop abruptly. They wouldn't fade out, they would switch off as if a valve had been closed. The most powerful evidence would be the object's movement. A natural explosion pushes things, but an engine provides unexplained acceleration. If we continued to track the object and saw it moving in a way that cannot be explained by the sun's gravity and the gentle push of sunlight alone, that would be the smoking gun. It would be the definitive signature of control. It would mean some other force, a non-gravitational force, was actively and perhaps intelligently at work. As 3i Atlas continued its plunge toward the sun, the scientific community was electric with anticipation. Every telescope that could be pointed at it was. We were watching, waiting and calculating. But as we discussed ground-based telescopes, and even our powerful space telescopes like Hubble and the James Webb Space Telescope were all fundamentally looking from the same general direction. We were seeing the object from the perspective of Earth, from the inner part of our solar system. To truly understand an object, you need to see it from multiple angles. This is as true for a sculpture in a museum as it is for a mysterious visitor from interstellar space. And as it happened, humanity had another set of eyes in the solar system. These eyes were not near Earth. They were orbiting Mars. We are talking about the Mars Reconnaissance Orbiter, or MRO. This incredible spacecraft has been circling the red planet for years, mapping its surface in breathtaking detail. And it carries a truly remarkable instrument, the high-resolution imaging science experiment known as HiRISE. This is essentially a massive telescope pointed at the ground. It is so powerful it can spot objects on the surface of Mars that are just a few feet across. It is the crown jewel of planetary observation. Someone, a brilliant engineer or scientist at NASA's Jet Propulsion Laboratory, realized they had a unique opportunity. Mars in its orbit was in a completely different position relative to 3i Atlas. From Mars, the MRO wouldn't be looking at the front or back of the object. It would be looking at its it would get a profile view. This was a long shot. The MRO and its HiRISE camera were designed to look down at a relatively stationary planet. They were not designed to track a tiny, fast-moving object against the blackness of deep space. It would require complex maneuvers, tilting the entire spacecraft, calculating the precise microsecond to open the shutter, and compensating for the object's own motion. It was an incredibly difficult feat of celestial navigation and engineering, and they did it. On October 2nd and 3rd, just as 3i Atlas was getting dangerously close to the Sun, the Mars Reconnaissance Orbiter successfully aimed its powerful HiRISE lens and captured images of the interstellar visitor. The importance of this data cannot be overstated. This was our before picture. This was the definitive high-resolution snapshot of 3i Atlas in its pristine pre-perihelion state. It was captured before the object's violent encounter with the Sun, before the fragmentation, before the outburst of gas and dust. This single image or series of images was the key. It was the baseline. It would tell us the object's shape. Was it long and thin like Oumuamua? Was it a simple round comet? Was it a cluster of objects? Was it already showing signs of stress? Was it venting small amounts of material that we just couldn't see from Earth? This profile view held the answers. By comparing this HiRISE image to the after pictures we would get from Earth-based telescopes after it passed the Sun, we could unlock the entire story. We could see exactly what changed. We could measure with incredible precision what parts of the object broke apart. We could understand the mechanics of its destruction. The data was captured, the commands were sent, the shutter opened, and the data was stored ready to be beamed back across millions of miles of space to Earth. The scientific community held its breath waiting for that priceless image to be processed and released. And then nothing. The data did not come. The days turned into a week. The object reached perihelion. It survived. It began to break apart. The after event was happening right now, and the before picture was nowhere to be seen. The reason was not a technical failure. It was not a solar flare or a lost signal. The reason was entirely frustratingly human. On October 1st, the United States government had shut down. Due to a failure to pass a budget, all non-essential federal agencies were ordered to cease operations. And NASA, the agency responsible for exploring the cosmos, the agency that had just captured the most important astronomical image of the decade, was deemed non-essential. The scientists, engineers, and data processors at NASA were furloughed. They were sent home. They were by law not allowed to work. They were not allowed to even check their email. The vast billion-dollar infrastructure of NASA's deep space network, the very network needed to download, process, and release the data from Mars, was effectively paralyzed. The images of 3I Atlas were in effect being held captive. They were trapped on a server, or perhaps still on the MRO satellite itself, waiting for a command that no one was authorized to give. The frustration in the astronomical community was palpable. It was a maddening, surreal situation. We were witnessing a once-in-a-lifetime cosmic event, and the most crucial piece of the puzzle was locked in a digital vault because of a political argument on Earth. This is when the calls began. The community, led by vocal figures like Professor Avi Loeb, began to publicly demand the data. They argued that this was not a matter of routine operations. This was a time-sensitive, irreplaceable observation. The data didn't just belong to a single agency, it belonged to humanity. Every day that passed was a day lost. The pressure mounted. Congresswoman Anna Paulina Luna, a member of the US Congress, publicly joined the call, demanding that NASA release the images. It escalated from a scientific complaint to a political issue. Here we were, a species capable of photographing a tiny speck from another star system from orbit around another planet, and we were tripping over our own feet. The consequence of this delay was devastating. We lost precious critical time. The key to understanding the entire 3I Atlas event was the comparison before versus after. And for weeks during the most critical phase of the event, we only had the after. We were trying to solve a puzzle with the most important piece missing. It's like trying to understand a car crash, but you're only allowed to see the wreckage after it's been cleared from the highway. You're forbidden from seeing the skid marks, the position of the cars at impact, or the dashboard camera footage from the moment before. You can guess what happened, but you can never know for sure. This data, this high-rise image, was our dashboard camera. It held the ground truth. Its delay meant that for the most crucial period, scientists were working in the dark, forced to speculate. Eventually the shutdown ended, the government reopened. The scientists and engineers returned to their posts, and the data was finally belatedly released. But the momentum was lost. The golden window where the before and after could be analysed simultaneously in real time had closed. This episode teaches us a powerful and humbling lesson. Our ability to explore the universe is not just limited by our technology or our budgets, it is limited by our own human systems. We have built extraordinary tools to look up at the stars, but we are too often distracted by our conflicts here on the ground. The universe will not wait for our politics. An object like 3I Atlas will not pause its journey because our governments are in disarray. The high-rise images were eventually studied, of course, but the delay itself became part of the story, a symbol of a missed opportunity, a time when our reach for the cosmos was held back by our own grasp. When we look up at the sky, we have a good idea of what to expect. Our scientific models built on centuries of observation tell us what is common and what is rare. We expect to see planets, comets, and asteroids following predictable paths, but what happens when the universe shows us something that doesn't just bend those expectations but seems to shatter them? This is the core of the problem that Professor Avi Loeb and others have pointed to. It's not just about a single strange object, it's about a pattern of strangeness that, when you do the math, points to something truly extraordinary. The problem is one of statistics, the science of chance, and in this case the numbers are telling us a fascinating story. Let's break down the first major anomaly, the simple, shocking size of the object the data refers to as 3I Atlas. Our very first interstellar visitor, Oumuamua, was relatively small. We estimate it was perhaps a few hundred meters long with a total mass of around 30 million tons. This made sense. Our theories about how solar systems are formed and how they eject material into deep space predict that for every massive object kicked out, there should be a truly gigantic number of smaller ones. It's like any collision, If you smash two large rocks together, you get 1,000,000 tiny pebbles for every one large boulder that breaks off. Therefore, our telescopes should see the pebbles, like Oumuamua, far more often than the boulders. We should be finding small objects all the time. Then 3i Atlas was observed. According to the data Loeb and his colleagues were analysing, this object was a monster. It wasn't a pebble, it wasn't a boulder, it was a mountain. The estimates placed its mass at over 33 billion tons. Its diameter was thought to be somewhere between 5 and 10 kilometers wide. This is 1,000,000 times more massive than Oumuamua. This discovery completely flips our expectations on their head. It's as if you decided to go fishing in a small pond expecting to catch a minnow, and on your very first cast you pulled out a full-grown blue whale. You wouldn't just be surprised, you would question everything you thought you knew about that pond. This isn't just unusual, it is statistically baffling. Based on our best models of the material floating around in interstellar space, the probability of seeing an object this massive, this early in our search for interstellar visitors, is incredibly low. Scientists calculated the odds. In the most generous optimistic scenario, the probability we can call this P1 for probability 1 of seeing an object this large is about 1 in 1,000. In a more realistic, less optimistic model, the odds are closer to 1 in 200,000. This means that for every one object the size of 3i Atlas, our models predict we should have already discovered at least 200,000 smaller ones. We haven't. We've barely found any. This massive disagreement is the first major crack in the "it's just a natural rock" assumption. But the problem gets deeper. An object's size is one thing, its path through space is another. This brings us to the second major anomaly, its truly bizarre orbit. To understand this, you have to picture our solar system. It's not a random scatter of planets. It's mostly flat. Imagine our solar system is a flat vinyl record. All the planets Earth, Mars, Jupiter to Saturn are orbiting the Sun in tiny grooves on this flat disk. This disk is called the ecliptic plane. Now an object coming from another star system from deep interstellar space should have a totally random path. It has no reason to know about our flat disk. It could come from above the record, below the record, or at any random tilted angle. The highway of our solar system shouldn't matter to a visitor from another part of the galaxy. The object 3i Atlas did two very strange things at once. First, it was in a retrograde orbit. This means it was travelling backward compared to the flow of all the planets. If the planets on the record are all spinning counterclockwise, this object was moving clockwise. This is extremely rare. It's like a car driving the wrong way down a high-speed one-way freeway. Second, and this is the truly baffling part, it wasn't just going backward, it was going backward while being perfectly aligned with the freeway. Its orbit was not random. It was strangely, uncannily flat, lying almost perfectly in that same ecliptic plane as our own planets. The orbital alignment was incredibly precise with a tilt of less than 5 degrees. Think about what this means. An object from another star, which should have a totally random path, just happens to fly into our system going the wrong way, but perfectly matching the flat layout of our system. The odds of this happening by chance are incredibly slim. It's like throwing a baseball from a mile away in a random direction and having it land perfectly on the pitcher's mound. The probability of an interstellar object just happening to have this specific rare retrograde but flat ecliptic path, we'll call this P2 for probability 2, is calculated to be about 1 in 500. Now we must look at these two facts together. This is the heart of the entire argument. In statistics, if you want to find the probabilities of two independent rare things both happening at the same time, you have to multiply their separate probabilities. We have P1, the probability of seeing such a massive object 1 in 200,000, and we have P2, the probability of it having such a specific weirdly aligned orbit 1 in 500. So what is the combined probability? What are the odds of both of these things being true for the same object? We multiply them. 1 in 200,000 times 1 in 500. The answer is 1 in 100 million. Let's pause and truly absorb that number. 1 in 100 million. This is the kind of probability that makes scientists stop, check their math, check it again, and then check it a third time. This is not just rare. This is statistically absurd. It's like a single person winning the grand lottery and then winning that same lottery again the very next week. If that happened, you wouldn't just say, "Wow, that person is lucky." You would immediately suspect the system was rigged. You would assume something else was going on that you didn't understand. This right here is Loeb's problem. The statistical anomaly is so powerful, so profound that it demands we reconsider our most basic assumptions. And the most basic assumption of all is that this object 3i Atlas was a natural object, a simple comet or asteroid randomly ejected from another star. When faced with a 1 in 100 million chance event, science gives us two main options. Option 1, we just witnessed a complete statistical miracle, an absurd fluke of chance, and we can just shrug, say, wow, and go on with our old models unchanged. Option 2, our models are not wrong, but our assumption is, the assumption that this object must be natural is the flawed part of the equation. If the object isn't natural, then these statistics become meaningless. The statistics only apply to rocks and ice chunks randomly kicked out of other solar systems. But if this object was, for example, an artificial construct, a piece of technology from another civilization, then its size and path would not be random at all. They would be chosen. Its creators could have made it large. They could have aimed it specifically along the ecliptic plane, perhaps, because that's the highway where all the interesting planets are. This is the central implication. The low probability doesn't prove it was artificial, but it does force us to put the artificial hypothesis on the table not as a wild fantasy, but as a sober logical alternative to believing in a 1 in 100 million miracle. This brings us to the very heart of the mystery. We have looked at the object, we have looked at the data, we have seen the anomalies, the speed, the size, the timing, the orbit, and now we are left at a crossroads, a place where science, philosophy, and imagination must meet. We are faced with a profound puzzle, and when the data does not fit our neat and tidy expectations, we are generally left with three, and only three possible paths. Let's walk through them one by one with the calm and rational attention this subject deserves. The first possibility is that we are simply lucky, or depending on your perspective, perhaps unlucky to be so confused. This is the statistical fluke argument. This path suggests that the universe is vast and chaotic, and given enough time, anything that can happen will happen. The models that suggest an object like 3i Atlas, so large, so fast, so early in our observational history as a 1 in 100 million event, are correct, and we just happen to be the civilization that won this strange cosmic lottery. It's like walking onto a beach and finding a single perfectly spherical pearl just sitting on the sand. It's possible, it doesn't violate any laws of physics, but it is so profoundly unlikely that you would be right to question it. To accept this first possibility, we must accept that we are witnesses to a statistical miracle. It's an intellectually honest position, but it is not a satisfying one. It relies on blind chance, and it teaches us nothing new other than that the universe is well random. This leads us to the second and far more common scientific position. This is possibility 2. Our models are wrong. This is the safe bet. This is the default setting for any good scientist. When your observations conflict with your theory, the theory is almost always the part that needs fixing. In this case, our models are our understanding of what the space between the stars is like. We assume it is mostly empty, punctuated by tiny grains of dust and the occasional small comet or asteroid ejected from a distant star system. We base this model naturally on the only system we know well, our own. We look at our own Oort cloud and our own Kuiper belt, and we project that onto the rest of the galaxy. But what if our solar system is not the template? What if we are the exception? If possibility 2 is correct, then 3i Atlas is not a 1 in 100 million event. It is instead the very first messenger from a population of objects we never knew existed. This possibility suggests that interstellar space is not empty and quiet. It suggests it is full of large planet-sized bodies, massive super comets, or rogue planets wandering in the dark. It would mean that planet formation is a far more violent, chaotic, and messy process than we ever imagined, with star systems routinely throwing out their largest children into the void. This is in its own way just as revolutionary as any other idea. It would rewrite the textbooks on astrophysics. It would mean that 3i Atlas is not an anomaly but a pioneer. It is the first, and soon we will see a second and a third and a fourth. We will have to update our models to include a vast unseen population of massive objects that fill the galaxy. This is a very compelling and perfectly scientific argument. It has a high bar to clear, it must explain how so many massive objects are ejected, but it is a testable, refutable hypothesis. And then there is the third path. This is the one that makes us lean in a little closer, the one that we are often afraid to say out loud in polite scientific company. Possibility 3. This was not a random occurrence. This is the hypothesis of intent. It is the suggestion that 3i Atlas is not a product of blind chance but of design. This is the artificial hypothesis. For decades we have been told that this idea is absurd, that it is the realm of science fiction and crackpots. But let's apply the same logical rigor to this path as we did to the other two. Let's reframe the problem. If we assume for just a moment that this is an artificial object, a probe, a ship, a relic, do its anomalies still look so anomalous? Suddenly the statistical puzzle seems to solve itself. Let's start with its trajectory. Why was this object travelling perfectly in the ecliptic plane, the same flat spinning disk-like area where all of our solar system's planets orbit? If it's a random comet from interstellar space, this is a mind-boggling coincidence. It could have come from any direction, from above our solar system, from below, or at any bizarre angle. But it didn't. It came in flat. But if you are an engineer building an interstellar probe, where do you aim it? You don't aim it at the empty dark north pole of a target star. You aim it directly at the ecliptic plane, the very place where the planets are the place where you are most likely to get a flyby, the place where any resident life would be. In this context, the object's path is not an anomaly, it is a sign of efficiency. It's exactly where we would send a probe. Now let's consider its size. Its massive kilometers-wide scale is perhaps its most statistically impossible feature as a comet. We have never ever seen a comet this large, even from inside our own solar system, let alone from outside of it. But if it's an artificial ship, a vessel designed to cross the immense emptiness between stars, it has to be large. It cannot be the size of a microwave. It would need to carry an enormous power source, whether it's fuel for a fusion engine or a massive sail to catch light. It would need powerful computers and navigation systems. Most importantly, it would need shielding. Travelling at high velocity, even a small grain of dust has the impact of a bomb. A vessel travelling for millions of years would need to be robust, perhaps kilometres thick, to survive the journey. Again, in this context, the object's enormous size is not an anomaly. It is a requirement of engineering. In this light, the statistical improbabilities suddenly vanish. The two strangest things about 3I Atlas, its path and its size, are precisely what we would expect to see from an artificial probe. The absurd hypothesis, it turns out, is the one that best fits this particular set of data. This line of thinking forces us to change our entire perspective on the search for extraterrestrial intelligence, or SETI. For over 60 years we have been listening. We have pointed our giant radio telescopes at distant spheres waiting to hear a signal, a beep, a message, a pattern in the noise. We have been listening for a call. But what if the first evidence is not a signal but an artifact? A radio signal is weak, it radiates out, follows the inverse square law, and gets fainter and fainter until it is lost in the cosmic static. A civilization might only broadcast for a few hundred years before moving to a new technology like we are. But a physical object, a message in a bottle made of titanium or some exotic alloy, an artifact endures. A probe, a ship, a piece of technology, it can drift through the galaxy for billions of years long after its creators have turned to dust. This object 3I Atlas challenges us to start looking as much as we are listening. We should be searching for the flotsam and jetsam of the galaxy, the technological relics that may be floating in the cosmic ocean. This brings us to a famous bet. Avi Loeb, a physicist at Harvard, who championed the artificial hypothesis for a similar object. Oumuamua has a public wager with the famous skeptic Michael Shermer. The bet is simple. Loeb believes we will find definitive, unambiguous evidence of an extraterrestrial technological artifact by the year 2030. Shermer, representing the mainstream skeptical view, has betted against him. This isn't just a game. This bet represents the frontier of this question. It is the tension between extraordinary claims require extraordinary evidence and the growing realization that our current data is already extraordinary. This brings us to our conclusion. Whatever 3I Atlas is, it is phenomenal. Whether it is possibility 1, 2 or 3, it is an object that has changed our view of the sky. If it is just a statistical fluke, we have learned that our universe is capable of surprising us in ways we can barely calculate. If our models of planet formation are wrong, we have learned that the galaxy is a far more chaotic and crowded place than we ever dared to imagine. And if it is an artifact, it changes everything. It means we are not alone. It means the answer to the Fermi paradox, where is everybody, is that they are here, or at least their relics are. This is why this object and others like it demand our full and passionate attention. We cannot shrug at the anomalies. We cannot look away because the implications make us uncomfortable. This is the very essence of science, to follow the data, even when it leads us into the most profound and unsettling territories. Whatever the answer is, 3I Atlas is truly extraordinary, and it demands an equally extraordinary investigation. And so we stand at the threshold. The journey with this mysterious visitor from across the stars has been one of mystery, of debate, and of pure scientific wonder. But now we are entering the final act, the most critical phase of our observation. The road ahead is where the data we've gathered finally becomes an answer. The most important time is right now. We're in the primary observation window, a period of intense focus that lasts from this very moment until the object's closest approach to Earth around December 19th. This is our last best chance to see it clearly before it sails past us and begins its long, cold journey back into the darkness of interstellar space. Think of it as a final high-speed flyby. All over the world, our most powerful telescopes, and even those operated by dedicated amateurs, are pointed at this one speck of light. This is the final exam. Everything that happens between now and that December rendezvous will be scrutinized, measured, and weighed against who great possibilities. Is this an extraordinary natural comet, or is it something else? To figure this out, scientists are not just guessing. They have a very specific, very logical checklist. This isn't a single yes or no question. It's a series of tests, and the answers, when put together, will paint a complete picture. First on that list is spectroscopy. This is a fancy word for a simple, beautiful idea. We look at the light coming from the object, and specifically from the material streaming away from it in those jets, and we pass that light through a prism. Just as a prism breaks white light into a rainbow, this process breaks the object's light into a barcode. Every chemical element, every molecule has its own unique barcode. We are quite literally reading the ingredients. What are we looking for? If that barcode screams water or carbon dioxide, the case for a natural comet becomes incredibly strong. This is precisely what comets are: dirty snowballs, ancient ice from the dawn of a solar system heating up and releasing gases. If we see carbon dioxide, it might tell us it came from a very, very cold place, even colder than where our own comets form. But what if the barcode is strange? What if it doesn't match water or carbon dioxide or anything we expect? What if it shows traces of metals or complex compounds that have no business being in a comet's tail? This is where the artificial hypothesis would gain a little ground. What does the exhaust of an alien engine look like? We don't know, but spectroscopy is our best tool to find out. Next on the checklist is velocity. How fast is this material leaving the object? This is another critical test. The models give us two very different scenarios. In the first scenario, the material is moving slowly, perhaps at 0.4 kilometers per second. That sounds fast to us, but in space it's a gentle puff. It's the speed you would expect from ice turning directly into gas, a process called sublimation. It's a passive, gentle push, like steam from a kettle. This would be a huge point in favor of the natural comet theory. But there's a second possibility. What if the material's measured at 50 kilometers per second? This is not a puff. This is a high-velocity expulsion. This is a propulsive event. This is not a kettle. It's a rocket. A speed this fast is very difficult to explain with natural ice turning to gas. It would imply a massive high-energy release, something more akin to an engine or an explosion. The difference between these two speeds is the difference between a passive object and an active one. Then we have the trajectory, the path the object is taking. We know that gravity from the sun is pulling it, but we also see it's being pushed by its own jets. We call this non-gravitational acceleration. This is normal for a comet. The real test is whether the push we see matches the jets we see. Imagine the object is firing jets out of its back, and it speeds up forward. That makes sense. But what if it's firing jets backward and it suddenly moves sideways? Or what if we measure the jets and calculate they should only give it a tiny push, but the object is accelerating far more than it should? This would be a true Oumuamua style mystery. It would mean there is a hidden force at play, a push we cannot see. That would be a profound and deeply puzzling discovery. There are simpler tests too. We need to check for fragments. Is it one single solid object, or is it a small cluster of pieces flying together? Many comets are not solid boulders. They are loose rubble piles that can break apart as the sun's gravity and heat torture them. If we see this object shatter, or if we see a family of smaller pieces accompanying it, the case is virtually closed. It's a natural comet breaking up, as they often do. If, however, it holds together as one solid piece, it tells us it's strong. Finally, we have the test of time. How do these jets behave? Do they gently fade as the object gets farther from the sun, like a natural process tied to heat? Or do they just stop? Imagine watching the jets and suddenly they switch off, as if someone flipped a light switch. Natural processes don't do that. They are messy, they fade, they hutter. An engine, on the other hand, is designed to turn on and off. This simple on-off test is one of the most powerful and simple ways to check for technology. This intense period of observation will end, but the story won't. In the long term, we have more to look forward to. The Juno spacecraft currently orbiting Jupiter is projected to get its own look at the object in March of 2026. And on the horizon, the new Vera C. Rubin Observatory in Chile will soon come online. This is a game changer. It's a machine designed to scan the entire sky night after night. It won't just find one interstellar visitor, it's expected to find hundreds. We will move from an age of single strange visitors to an age of population studies. This object is the preview. Rubin will deliver the full catalogue. And of course, there is the Galileo project. This is a private scientific group specifically organised to search for evidence of extraterrestrial technology for artefacts. They are watching this object with great interest because it is the first real test of their mission. This brings us to the final most important point. We stand on the verge of an answer, and that answer, whatever it is, will be profound. If, as is most likely, the data confirms this object is a natural comet, a visitor from another solar system, we will have learned something incredible. We will have confirmed that the building blocks of solar systems, and perhaps the building blocks of life, are not isolated. They are shared. The universe is a connected place with material from one star system being thrown across the void to land in another. We are holding a piece of another star's family in our hands. And if the answer turns out to be artificial, that is a moment that changes human history. It would mean that interstellar travel is possible, and that someone or something is already doing it. It would mean that we are not alone in the most direct and unambiguous way. It would change our science, our philosophy, our art, and our entire perception of our place in the cosmos. Either way, we win. Whether this is an extraordinary piece of nature or the first glimpse of a new reality, we will have learned something deep and fundamental about the universe. The true story here is the human one. It is the story of our own curiosity, our drive to collaborate across borders to build incredible machines and to point them at the sky, all just to know. This object is a gift. It has crossed an unimaginable ocean of time and space, and in its final moments in our neighbourhood, it is holding up a mirror reflecting back at us. Our own deepest, most human question, are we alone? We are about to get a clue, so keep watching, keep wondering, and as always, keep looking up.